When a Linux system suddenly refuses to start a service, or when the whole machine feels partially broken even though it booted, the root cause is often not a single application bug, but a failure in the glue that connects the operating system to its services. For beginners, this category can be frustrating because the symptoms can be indirect. A website is down, a backup job never runs, a login is slow, or a network feature silently disappears. Behind the scenes, services depend on a service manager to start them, supervise them, and record why they failed, and on a consistent execution environment that includes things like path and driver availability. If those foundational pieces are misconfigured or incomplete, the system can behave like it is haunted, with errors that look unrelated but share one cause. The goal in this episode is to give you a calm first response model for system and service failures that helps you distinguish between systemd unit issues, environment path issues, and missing drivers. When you can classify the layer quickly, you avoid chasing symptoms and you regain control of the system's behavior. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A good starting point is to treat a service as a contract about what should be running and under what conditions. In modern Linux distributions, the most common service manager is systemd, and it uses unit files to define services, timers, sockets, mount points, and other managed objects. You do not need to memorize every unit type to troubleshoot effectively, but you do need to understand that a unit file is a recipe that systemd follows. It tells systemd what executable to run, what arguments and environment to supply, what dependencies must be started first, what user context to run under, and what constitutes success or failure. When a service fails to start, the unit recipe is the first place where misalignment can occur, because the recipe might reference a path that no longer exists, a user that is missing, a dependency that is not available, or an environment variable that is wrong. Beginners often think the service itself is broken, but many failures are actually recipe failures. This perspective is powerful because it shifts your attention from blaming the program to verifying whether the manager is being told to start it correctly. Systemd failures also highlight the difference between a service that never starts and a service that starts and then immediately exits. These situations feel similar to a user because the service is not running, but they imply different underlying causes. If systemd cannot even launch the process, the failure is often about the execution path, permissions, missing files, or missing dependencies. If the process launches and then exits, the failure might be internal application logic, a configuration issue, or a resource constraint that causes the program to give up. In first response triage, this distinction matters because it tells you whether to focus on systemd's ability to execute the program or on the program's own runtime behavior. Beginners sometimes waste time tweaking unit files when the application is crashing due to misconfiguration, or they waste time editing application configuration when systemd is simply pointing to the wrong executable path. The calm way to proceed is to identify which phase is failing, launch, or run. Once you know that, your next checks become much more targeted. Dependency ordering is another reason systemd units fail, especially after reboots, because many services require other components to be ready first. A database service might need storage mounts to be available, a web service might need the network to be ready, and a security service might need keys or permissions established before it can start. If systemd is told to start a service before its prerequisites are ready, the service may fail, even though it would succeed if started later. Beginners sometimes interpret this as a flaky service, but it is often a dependency definition problem where the unit file does not accurately describe what it needs. The key concept is that systemd is not reading your mind. It is following declared relationships. If those relationships are wrong or incomplete, systemd may start things in an order that makes sense to it, but not to your service. This is why service failures can feel intermittent across boots. Small timing differences can determine whether a dependency is ready in time. A disciplined ops mindset treats dependency declarations as part of reliability engineering because correct ordering reduces unpredictable startup behavior. Now let's connect systemd unit failures to the execution environment, because many services fail simply because they cannot find the programs they rely on. One of the most common culprits is the path environment variable, which determines which directories are searched when a command is executed without an absolute path. Beginners sometimes assume that if a command works in their interactive shell, it will work in a service, but services often run with a different environment. A unit might launch a program with minimal environment variables, and the path available to it may be shorter or different than what your user session has. If the unit recipe calls a helper command without specifying its full path, systemd might not find it, even though you can find it in your terminal. This creates a confusing symptom where a script works manually but fails when run as a service. The conceptual lesson is that interactive convenience is not the same as non-interactive reliability, and relying on implicit path behavior can make services fragile. Path misconfiguration can also affect the system outside of services, especially when administrators make changes to path globally without understanding scope. If path is modified incorrectly, users might run the wrong version of a tool, scripts might resolve to unexpected binaries, and automation might fail because commands that used to be found are no longer reachable. There is also a security angle here, because a poorly controlled path can cause a system to execute unintended programs if a malicious or accidental file appears earlier in the search path. For beginners, the key is to understand path as both a convenience feature and a risk surface. In services, the safest approach is often to treat the execution environment as explicit rather than assumed, ensuring that critical paths are defined and that the unit recipe does not depend on interactive shell customization. When you adopt that mindset, you stop being surprised by the difference between running something manually and running it under a service manager. You also develop habits that prevent subtle bugs from showing up only in production, which is where they are hardest to diagnose. Missing drivers are the third major category in this episode, and they can cause service failures that look like application problems when the root cause is that the operating system cannot interact with hardware correctly. A driver is the software that allows the kernel to communicate with a device, such as a network interface, storage controller, graphics adapter, or specialized hardware. When a driver is missing, outdated, or incompatible, the device may not appear, may not behave reliably, or may fail under load. This can cascade into service failures because services depend on devices. A network-dependent service might fail because the network interface is not functioning, or a storage service might fail because the storage controller is not available. Beginners sometimes chase the service configuration when the real issue is that the underlying device layer is incomplete. The triage habit is to ask whether the service depends on a device that might not be present or might have changed, especially after updates, hardware changes, or virtualization migrations. When you include drivers in your hypothesis set, you can connect symptoms that otherwise feel unrelated. Driver issues also illustrate the difference between a system that is configured correctly and a system that is capable of fulfilling that configuration. You can have a perfect configuration for network services, but if the network driver is missing, the system simply cannot deliver networking. The same idea applies to storage. This is why missing drivers can appear after kernel updates or after moving a disk image to different hardware. The new environment might require a different driver, and until the kernel has that driver available, the device layer is incomplete. A beginner can feel confused because nothing in the service configuration changed, yet the service fails. The correct interpretation is that the service is a client of underlying capabilities, and those capabilities can change when the kernel or hardware changes. In first response triage, you use the timing of changes as a clue. If failures began immediately after a kernel update or hardware move, driver compatibility becomes more likely. This change awareness prevents you from assuming the service logic is at fault when the platform changed underneath it. System and service failures can also be caused by missing configuration files, missing permissions, or missing runtime directories. But the reason we emphasize systemd, path, and drivers is that they represent common shared dependencies that can break many things at once. When systemd units fail broadly, you may see multiple services refusing to start, and the machine may feel partially unusable. When path is broken, scripts and helper commands might fail across many services, and you might see a pattern of commands not found even though the programs are installed. When drivers are missing, Entire categories of capability disappear, such as networking, storage access, or device discovery, leading to failures that look like application errors but are actually platform errors. The key skill is pattern recognition across scope. If one service fails, you investigate that service's contract. If many services fail, you suspect a shared dependency like system deconfiguration, file system availability, or a broad environment issue. If failures cluster around a specific capability like networking, you suspect driver or hardware layers. This scope-based reasoning is a core operations skill, and it is exactly what helps you respond quickly without guessing. A useful mindset for first response is to treat systemd as a source of truth about service lifecycle because it records what it attempted and what happened. That record lets you distinguish between failure to execute and failure after execution, between dependency issues and internal crashes, and between repeated restart loops and one-time failures. The same mindset applies to environment differences. You assume the service environment is minimal unless proven otherwise, so you do not rely on interactive path behavior or user-specific settings. For drivers, you treat hardware capability as a prerequisite and consider whether platform changes altered which drivers are needed. The common theme is explicitness. Services become reliable when their dependencies are explicit, their environment is explicit, and their platform assumptions are explicit. Beginners often write scripts and services that work only because their personal interactive environment fills in missing pieces. When you move that work into system automation, those implicit assumptions fall away and failures appear. Learning to remove implicit assumptions is what turns a learner into a reliable administrator. There is also a safety dimension to how you recover from these failures, because quick fixes can create long-term instability. For example, a rushed path change might make one service work, but cause another to run the wrong binary later. A rushed unit file edit might bypass a dependency check, causing the service to start in an unsafe state. A rushed driver workaround might hide the real issue that a kernel update created incompatibility that should be addressed properly. The better approach is to restore correct contracts rather than to suppress symptoms. If a unit file is wrong, the fix is to align it with the real executable path and dependencies. If path is missing, the fix is to make the service environment explicit rather than to rely on global hacks. If a driver is missing, the fix is to restore platform capability at the kernel layer rather than to force services to behave as if the device exists. This mindset is what separates recovery from improvisation. In operations, improvisation sometimes gets you through the moment, but it often leaves hidden debt that resurfaces later. As we conclude, you should be able to describe these failure modes in a way that guides action rather than creating fear. Systemd unit failures are often recipe failures, where the unit file references the wrong paths, missing dependencies, incorrect ordering, or incorrect permissions, and the first response goal is to determine whether the service failed to launch or launched and then exited. Path misconfiguration creates mismatches between interactive success and service failure, because non-interactive environments may not search the same directories, and it also creates security and correctness risks when the wrong binaries are executed. Missing drivers remove platform capabilities and can make services fail even when their configuration is correct, especially after kernel updates or hardware changes. First response triage is about classifying which layer is failing, using scope and timing to narrow likely causes, and restoring explicit contracts rather than applying quick, risky hacks. When you develop this classification habit, service failures stop feeling like a pile of unrelated errors and start feeling like structured problems with clear layers, which is exactly the mindset Linux Plus aims to build.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.